Chapter 25 Gaussian Coordinates. According to Gauss, this combined analytical and geometrical mode of handling the problem can be arrived at in the following way. We imagine a system of arbitrary curves, see figure below, drawn on the surface of the table. These we designate as U-curves, and we indicate each of them by means of a number. The curves U equals 1, U equals 2, and U equals 3 are drawn in the diagram. Between the curves U1 and U2, we must imagine an infinitely large number to be drawn, all of which correspond to real numbers lying between 1 and 2. We have then a system of U-curves, and this infinitely dense system covers the whole surface of the table. These U-curves must not intersect each other, and through each point of the surface, one and only one curve must pass. Thus, a perfectly definite value of U belongs to every point on the surface of the marble slab. In like manner, we imagine a system of V-curves drawn on the same surface. These satisfy the same conditions as the U-curves. They are provided with numbers in a corresponding manner, and they may likewise be of arbitrary shape. It follows that a value of U and a value of V belong to every point on the surface of the table. We call these two numbers the coordinates of the surface of the table, Gaussian coordinates. For example, the point P in the diagram has the Gaussian coordinates U equals 3 and V equals 1. Two neighboring points, P and P prime, on the surface correspond to the coordinates P of coordinates U and V, P prime of coordinates U plus DU, and V plus DV, where DU and DV signify very small numbers. In a similar manner, we may indicate the distance, line interval, between P and P prime, as measured with a little rod, by means of the very small number ds. Then, according to Gauss, we have ds squared equals g11 du squared plus 2g12 du dv plus g22 dv squared, where g11, g12, g22 are magnitudes which depend in a perfectly definite way on U and V. The magnitudes G11, G12, and G22 determine the behavior of the rods relative to the U-curves and V-curves, and thus also relative to the surface of the table. For the case in which the points of the surface considered form a Euclidean continuum with reference to the measuring rods, but only in this case it is possible to draw the U-curves and V-curves and to attach numbers to them in such a manner that we simply have ds squared equals du squared plus dv squared. Under these conditions, the u curves and v curves are straight lines in the sense of Euclidean geometry, and they are perpendicular to each other. Here, the Gaussian coordinates are simply Cartesian ones. It is clear that Gauss coordinates are nothing more than an association of two sets of numbers, with the points of the surface considered, of such a nature that numerical values differing very slightly from each other are associated with neighboring points in space. So far, these considerations hold for a continuum of two dimensions, but the Gaussian method can be applied also to a continuum of 3, 4, or more dimensions. If, for instance, a continuum of 4 dimensions be supposed available, we may represent it in the following way. With every point of the continuum, we associate arbitrarily 4 numbers, x1, x2, x3, x4, which are known as coordinates. Adjacent points correspond to adjacent values of the coordinates. If a distance ds is associated with the adjacent points p and p prime, this distance being measurable and well defined from a physical point of view, then the following formula holds. ds squared equals g11 dx1 squared plus 2g12 dx1 dx2 and so on plus g44 dx4 squared, where the magnitudes g11, etc. have values which vary with the position in the continuum. Only when the continuum is a Euclidean one is it possible to associate the coordinates x1, x4 with the points of the continuum, so that we have simply ds squared equals dx1 squared plus dx2 squared plus dx3 squared plus dx4 squared. In this case, relations hold in the four-dimensional continuum which are analogous to those holding in our three-dimensional measurements. However, the Gauss treatment for ds squared, which we have given above, is not always possible. It is only possible when sufficiently small regions of the continuum under consideration may be regarded as Euclidean continua. For example, this obviously holds in the case of the marble slab of the table and local variation of temperature. The temperature is practically constant for a small part of the slab, and thus the geometrical behavior of the rolls is almost as it ought to be according to the rules of Euclidean geometry. Hence, the imperfections of the construction of squares in the previous section do not show themselves clearly until this construction is extended over a considerable portion of the surface of the table. We can sum this up as follows. Gauss invented a method for the mathematical treatment of continua in general, in which size relations, distances between neighboring points, are defined. To every point of a continuum are assigned as many numbers, Gaussian coordinates, as the continuum has dimensions. This is done in such a way that only one meaning can be attached to the assignment, and that numbers, Gaussian coordinates, which differ by an indefinitely small amount, are assigned to adjacent points. The Gaussian coordinate system is a logical generalization of the Cartesian coordinate system. It is also applicable to non-Euclidean continua, but only when, with respect to the defined size or distance, small parts of the continuum under consideration behave more nearly like an Euclidean system. The smaller the part of the continuum under our notice.